Hello and welcome to this video. This is the third video of the module Electrostatics, which is part of the course on physics for class 12. In the last video we have seen about the Coulomb's law and some of its examples. In this video we shall be looking at the electric field, the concept of electric field. Before Faraday's time, the force acting between charged particles was thought of as a direct and instantaneous interaction between two particles. This view was known as the action at a distance view, where it was assumed that there was a particle interaction. So if I have a point charge over here and a point charge over there, then there is a force between them. If for some reason one of the charges is moved, the force changes instantaneously. This is also true for the gravitational force. However, this poses some problems. This does have certain consequences which are not in line with what we know is valid. Specifically, it turns out to be the case that if this was true, the action at a distance picture was valid, then what will happen is that information might travel with a speed which is more than that of light in free space. However, it is known that the maximum speed with which an information bearing signal can travel is that of light. Now, what might be the problem? Let's take an example with the gravitation part. Suppose, for example, that the sun vanishes. We know that the earth moves around the sun because of the gravitational attraction providing the necessary centripetal acceleration, the gravitational force rather providing necessary centripetal acceleration. So what happens if, for example, the sun vanishes abruptly? The earth, how will it move? Because the sun is no longer there, and if we assume that the action at a distance picture is valid, then the earth should leave the circular path and go tangentially. However, there is a problem. The fact that the sun has vanished, this information cannot reach the earth before light actually does. Now, light takes around 8.2 minutes to reach the earth, which means that the information that the sun has vanished is going to actually reach the earth only after 8.2 minutes. So what happens between those 8.2 minutes, the vanishing of the sun, and after, 8.2 minutes have passed after that? Because so far, according to the action of the distance picture, because the sun has gone, the gravitational force has also gone. And that means that there is no agent which can provide the necessary centripetal acceleration to the earth, and so the earth can't move along the circular path. Okay. However, as I said, the earth does not know that the sun has vanished till 8.2 minutes, and only then it will leave that circular path. This is a contradictory situation, okay, a paradoxical situation actually. Now we can talk about charges as well. For instance, say that we have one point charge over here on the earth and the other point charge is at the sun. Okay, so again the same thing. If the charge on the sun vanishes, then the force between these two charges is gone. However, that will imply that the information has traveled instantaneously. Okay, so that is why this picture is problematic actually, because it doesn't go well with one of the most fundamental ideas that we have today, and that is the fact that any kind of information can't reach any place faster than the speed of light actually. So to overcome this difficulty, the current view that is held today is that of the idea that a particle creates a field around itself, and this field is with which the other particle interacts. Fine. So the view is that of a particle field particle. A particle creates a field. It could be electric field, as we shall see, or it could be gravitational field as well. And this field is with the quantity with which the other charge interact, actually other particle interact. In fact, as we shall see, this will actually remove the problem of that contradiction that we were having with the action at distance picture. Actually, let us talk about the electric field itself. When you have a point charge placed at some location, it modifies the space around itself in some way. We shall see exactly how it does so. And we say that it creates an electric field around itself. This has been shown or suggested in this case, not exact diagram, but it's a suggestion that how this might be by this shaded portion over there. And when another charge, in this case Q2, comes in that region, or it comes in the field, then there is a force which it experiences. So in this sense, the electric field is just acting like a mediator of the force between the charges. Okay. Now that means therefore that finding the force between two charges, therefore this reduces to two problems. Okay. The first task is to find the electric field of the source charges, and the second part is then to find the force given the electric field which will exert the force on a test charge, actually. So basically you find out the electric field because of the source charges, and when a test charge is there, then we find out the force which the electric field exerts on the test charge. So this basically becomes a two-way task over there. Now if we wish to determine the electric field at a point, there is an operational definition which we require. Now you see that in physics we always need to have operational definitions. The operational definition does not only tell us what a quantity is, but also tells us how to measure that quantity. Okay. In this case, we are therefore looking at a definition for the electric field. Now, to operationalize or to just find out the electric field at a certain point in space, suppose there is a point in space over here, and I would like to find out what is the electric field at this point. It may be because of some other charges over there which may be around in this region. Fine. So the idea in this case is to place a small test body which carries a test charge, which I am going to call as capital Q. Put this test charge at a point, at whatever point I am looking to find out electric field. Measure the force F that acts on the body, the test body. Then the electric field at that particular point will be, by definition, the force divided by the charge, the test charge. So the electric field E is nothing but F vector upon Q, the test charge. Now E is a vector field, actually. It's a vector quantity, in fact. The reason is that because the force, that is a vector, but the charge is a scalar quantity, as a result of which the electric field is a vector field. Its SI unit is Newton per Coulomb, which we also call as volt per meter. Now in this case we have used a test charge, which in this case is capital Q, to determine the electric field E at a certain point. But you should keep in mind that the electric field itself does not depend on the test charge capital Q. What it does depend on is the source charges. Okay, the test charge is just a way to sense the field, but the test charge does not affect the electric field as such. Though what might happen is, if we suppose for example that we have a charge configuration that creates a certain electric field, and I am trying to measure the electric field at that certain point. Now what might happen is, when I bring a large enough test charge, that test charge can actually disturb the charge configuration which was creating that electric field, as a result of which the electric field that we now measure is no longer the field that we are actually looking for. It has changed. As a result of which, what we should try to do in this case is try to take the test charge as small as possible, so that we might avoid this disturbance of the charge configuration, which will change the very quantity which we are trying to measure. So we could actually write down in this case that the electric field is F by Q. However, we shall try to take as small charge as it is possible. So we could just say this as a limiting case when the test charge Q tends to 0. Okay, though we know that the lowest or the least charge that we could take up as a test body is nothing but the electronic charge. We can't go any lesser than that by the way. Just however, for the sake of definition, we just try to make the test charge as small as possible. That will actually make sure that we are not disturbing the electric field that we are trying to measure. In any case, whatever quantity you get F by Q as is the electric field at a certain point over there. Okay, that there is no doubt about that. That's by definition the electric field at a certain point. Okay. Now, conversely, if there is an electric field in the region, in some region there is an electric field E, we know that. Okay, we know that some charges have produced an electric field E in some part of the region. Now if I put another charge Q over here, this is not one of the charges which have produced the electric field. This is something else. Okay, another charge. In this case, this charge will actually experience a force, and that force we could obtain by the same definition but writing in a different way, as the force F as Q into E. So what I do over here is we obtain the force by multiplying the charge Q with the external electric field. Remember that a point charge or any charge cannot exert a force on itself. Okay, so when I talk about the force on a point charge by an electric field, this electric field is a field which is produced by some other charges, and we are getting the force on a different charge by placing it at a known point in the electric field actually. Fine. Let us try to find out, by applying this definition of the electric field out of a point charge actually. How does, or what way, or how can we find out the electric field due to a point charge? Now to do that, the idea is pretty simple. As we know, if I wanted the electric field because of this point charge which we have over here at a certain location, which is this point, it is characterized by the position vector r, which is the position vector of the point of interest with respect to the source charge Q in this case. So as per the definition, what I need to do is to put a test charge capital Q. I place a test charge capital Q at the relevant point where I am trying to measure the field. Then I need to find out the force on this test charge. Now that follows from the Coulomb's law. The force is nothing but 1 by 4 pi epsilon naught Q multiplied by Q divided by r square along r cap. I am assuming the test charge to be positive and this given source charge also to be positive, so that the force on capital Q, the test charge, will be away from this source charge because it's going to repel it actually, as a result of which the direction is along r cap vector, the unit vector along the position vector r actually. Now what I need to do is, in order to find out the electric field, I need to divide this force by the test charge, capital Q. So I do that, as a result of which the electric field turns out to be this. So because of a point charge, therefore the electric field is nothing but 1 by 4 pi epsilon 0 q by r square along r cap direction. So it basically still varies as 1 by r square. Though it's very much like a Coulomb's law, except for the second charge is not present. We might think that we have reduced or replaced the second charge as just 1 Coulomb actually, which implies we can think of the electric field as a force on a unit test charge in fact. So this becomes a formula to find out electric field for a point charge. If Q is positive, then this field is going to point away from the source charge, while if Q was negative, then this r cap, this minus sign will appear over here, which would multiply it with r cap vector. So that will be implying that the direction is actually towards the charge in fact. Fine. So therefore for a positive point charge, the electric field at any location points away from the point charge, while for the negative charge it points towards the point charge in fact. Fine. And the variation is just 1 by r square. Obviously it implies that if I go at a point which is double the distance from a previous location, the electric field simply becomes 1/4 of the magnitude in fact. It goes down. Okay. Now what to do if I want to find an electric field of a number of charges? So because the forces, they do follow the principle of superposition, it follows that the electric field also follows the principle of superposition, which means therefore that if I wanted to find out the electric field because of the n point charges, for instance, if I want the net or the resultant electric field due to a group of n point charges, the idea will be to first calculate EI. EI in this case represents the electric field of the ith point charge at the point of interest. So electric field due to the ith charge at a given point, as if it were the only charge present, which implies that the presence of the other charge doesn't matter as far as the electric field of a point charge is concerned. It will still be the same actually. Fine. Now then we just add these separately calculated fields vectorially to find out the resultant field E at the point. Remember this, we need to add it in a vectorical manner. We cannot add just the magnitude unless until we know that all the fields are in the same direction. If I knew that okay, all the electric fields because the individual point charges are in the same direction, then obviously I can just add the magnitude. Otherwise we must add them up according to the rules of the vector addition actually. Fine. In the equation form, we could just write down this simply as E vector, which is the net or the resultant electric field, as E1 plus E2 plus E3 so on, which in the summation notation I have written down this manner. It's just asking us to add all the electric fields that we have just calculated for the individual point charges actually. Fine. Now what if the charge distribution is not discrete? Implies that it's not only a collection of point charges, but rather a continuous one. Okay. Now remember that we said that charge is actually quantized. Yet we can in this case consider charge to be practically continuous, because the fact that the electronic charge is too small and therefore the quantitation is not apparent, not visible as such when we take up charges in the bulk. I mean, say for example, if I take some charge body, usually the charge will be so large number of times of the electronic charge that it is practically, I mean, say useful to take this as simply as a continuous body, like a like a jelly for example, which can be rubbed around. Fine. So in that case, if the charge distribution is a continuous one, for example, then what we can do is we can divide the body into very small segments, elementary parts, each of them can be thought of as a point charge. So I'm just dividing the charge into infinitesimal elements, very small elements, dq. Then computing the electric field dE due to each of these elements, assuming that they are point charges actually, and then integrating over all the charge elements. In this case, therefore, we need to integrate. When I add up the discrete quantities, we have the summation, but when I add continuous quantity, then we have an integration. Fine. So in this case, we need to integrate over the entire body wherever charged all the electric fields dE produced by the elementary point charges. Okay, that will be the way to be computing the electric field of many point charges. We shall see some examples later on. Now, how do we represent the electric field, by the way? For example, let's take a point charge. How do we represent the electric field? Electric field is a vector field. So what I could do, for example, is around this point charge q, I could choose to draw vectors. So for instance, I could draw, close to the point charge, the vectors will be longer in length because they will have more, the field will be stronger actually. But as I go away, the field becomes less, and therefore the corresponding vectors become small and small, the direction away from the point charge. This can be done at every point. I could draw vectors which are going to get subsequently or successively smaller. Similarly, on this side as well, we could have longer vectors, then shorter, and same thing continues all around the point charge. I can obviously draw many vectors actually. It will be definitely difficult to draw. Exactly how many vectors I draw depends on how sharp my pencil is and how energetic I am actually. So if I just draw enough line, it can give me a sense of how the field might vary around. Fine. This is one way. Obviously, I can draw a lot of vectors in this case. However, what we can do also is, instead of having this vector, just join these continuously. So I just join them. Now these are becoming lines. They are no longer vectors, but rather they are lines. They have become lines of force, or the electric field lines actually. Fine. Now in this case, you see that because these are no longer vectors, the directions are still indicated by the arrows that we have over here. But what about the magnitude? Earlier we had the magnitude of the electric field encoded in the length of the vectors, but now, as we have thrown away that vectors, I have not drawn just lines, so I have thrown away the information regarding the magnitude of the field itself. However, in this case, what we can do, for example, is we can come up with the fact that number density of the lines implies where they are more denser. Okay, this number density of the lines now will encode the information regarding the strength of the field actually. The number density is a number of lines per unit of cross section area. So basically, the electric field lines, or the lines of force, which is what Michael Faraday used to call them, they are a way of pictorially representing the electric field pattern of a configuration of point charges or charges basically. The electric field lines are drawn in such a way that the tangent drawn at any point of the field should be along the direction of the net electric field at that point. This is important. We need to draw the lines in such a way that at any point, if I draw a tangent line, then that should be pointing in the direction of the net electric field at that particular point, the resultant. Okay, that's important. And secondly, the number density of lines, implying the number of lines per unit of cross section area, represents the magnitude of the electric field. So wherever there is a weaker electric field, the line should be far apart, and where there is a stronger or denser electric field, the line should be close by. Okay, for example, I could have a field pattern like this, for instance, where the field lines becomes quite wider apart farther down this side, and they are very crowded near this region over there, which implies that this part over here has a stronger electric field and this part over there has a weaker field. Okay, this is very similar to what streamlines were drawn over there in fluids. I hope you remember that. Now, as we just have seen, the electric field lines near a point charge, it points radially, okay, radially outward for a positive point charge and radially inwards for a negative point charge. Fine. In order to draw the electric field lines for a configuration charges, the idea what we do is we just first of all select a convenient number of lines per unit of charge. So for example, I take 8 lines for a charge Q, I must take 16 lines for a charge 2Q. So there is a sample rate that we can have. Obviously, we can define infinite, we can draw infinitely large number of lines actually. However, we must start with a sampling value, a sample, and then proceed with that particular sample. Okay, so we shall just agree. Okay, otherwise if I draw so many lines that practically fill the page, then there is no information at all. So we just choose a sample first of all and then do accordingly. Now what we shall do is, near a point charge which is positive or negative, doesn't matter, but near a point charge we shall draw the lines practically radially, because near a point charge the influence of this point charge is going to overcome everything else, as a result of which we shall start by drawing radial lines near a point charge, and as we go away we should just work out the net electric field by looking at the few vectors and then accordingly draw the tangent lines. So this is going to be definitely a cumbersome task, but we can just see a few examples. But keep in mind that the electric field lines are actually lines which are in space. We are just drawing them in a plane, by the way, but they will technically be lines in the space. Okay, they are three-dimensional in space lines actually. Now, field of point charge, let us consider first of all positive point charge. You have already seen over there. For a positive point charge, the field will simply radiate outwards, okay, radially, because it's symmetric in all directions over there. So it must be radial for a positive point charge, while for negative it's simply going to be inwards. So that's going to be radially inward over there. This is not a very difficult task to see actually. Fine. But what if I have, there are two identical point charges, by the way. If I have two identical point charges, say both are positive as such, then the idea is that first of all you can see that near the middle, at the center of this over there, these two will produce the same electric field in magnitude, direction will be opposite. So the field will cancel out at the middle. There is no field at the middle, and so we cannot have any lines through the middle. In fact, near about I start with drawing, radial lines over there, practically radial, near each of the charges. But then as I go, for example, if I just over here, which is a point closer to the charge on the left over there, the vector of the electric field, because this left charge will be pointing this way, while that because the right one will be a bit smaller, it will be radially away but a bit smaller. Fine. And therefore the vector sum will be something like pointing this direction, which implies therefore that at this particular point the tangent line must be like this. So it starts and it bends like this. Fine. We can definitely do this at number of points, and the end result what we have is something like this. Okay, as we see, near the region which is the middle, the field lines are trying to avoid because simply there is no field at that point. On the other hand, if I had equal and opposite point charge, then what happens? This is basically a dipole in this case. So in this case what happens is, we can see that in between them there is an electric field at every point, which implies at least in between the field line has to be like this. Okay, because at every point there is a field over there. As if I look at, for example, a point which is entirely on a perpendicular bisector, I see that because of the positive point charge, the electric field points this way, while for the negative one is pointing exactly this way, and these two are equal in magnitude over here. The resultant therefore becomes horizontal, which means that in this case, at the middle, on this equatorial plane that we have over there, the equatorial plane, the electric field lines must cut horizontally everywhere. So it should be something like this, like very much like a bar magnet actually. Obviously, if I take this side, this will be just entirely going away, in this case going to be into this charge, and we can just keep on drawing a number of lines. The result is that we end up getting something like this pattern. Fine. That's for equal and opposite point charges. Now if I have two different charges, this becomes a bit complicated. Like for example, if I have 2-point charges, which is plus 4q and minus q, it's a good exercise in this case to show that we'll be actually able to find over here there's a charge 4q plus and there's a charge minus q somewhere over here. So first of all, in this case, turns out there's some point on the right side over here, the electric field turns out to be 0. You might try to just find at what point exactly the electric field is 0 in this case. But the fact is that this region will be avoided in this case. Field lines, more lines will be emanating from this 4q, less will be from minus q. Some lines definitely go straight over here, but the problem is that some lines, because the plus 4q is very large, so far from, if I look at from quite far apart, the field lines will seem to come radially over there, all over the entire space, fine. So the point is that the electric field, some of them, this later field lines, they will try to go this way, but then they'll have to bend and just go away, avoiding this region. Some will just go like this, difficult again to draw, but then we can just work out with a bit of practice over there. The field pattern is quite interesting. It just seems to avoid this particular region. As I said, very, very far away, they will look practically like, in this case, that they are coming out radially, fine. So the end result is what we end up getting, something like this, what we have, fine. You should also notice that this electric field lines, when I draw, because at every point we have the net field, the direction of the line is along the net field over there. That means that two lines can't intersect over there. If I had to have intersection of two lines, it implies at the intersection point there are two resultant which can't happen. In fact, that implies that the electric field lines cannot cross. Okay. In fact, as I said already, this is in fact a 3-dimensional curve. So it will be useful in this case to actually visualize in 3D space. Okay. This is a short presentation of this. You can see this is for a positive point charge, where the fields are basically emanating radially outwards from the point charge in this case, or you can take a negative, doesn't matter actually. The field line direction arrow won't be there in this case, so they are basically radial lines. Now there we have two identical charges, positive or negative, doesn't matter, but they are identical. As you can see in this case, the field line kind of repel each other. They tend to repel each other, avoiding the nearby, the middle region. In fact, okay. In fact, you can see that this. I mean, Faraday has in fact visualized electric fields more in terms of the lines over the lines of force. He was not a very trained mathematician, so he used to visualize them in terms of these lines. In fact, okay. Then we have, for example, this is for a dipole, as we just saw. This is a very familiar, this field pattern, which is very similar to that of bar magnet as well. It's an axis symmetric field. If you take up a line joining the two charges, and if I just rotate the entire field pattern about that line, it remains the same in fact, which is what we have in this case, fine. And the last example that we have is the one which we considered, 4q and minus q, of that one, where we have some region in this case on the right side where the electric field is 0. It's difficult to see in this case particular thing, but at least we could see the pattern of the field lines. They do indeed go in a very similar manner that we just saw over there, fine. So that those are a few examples that we have. Now I think that will be all in this particular video actually. We shall see some example in the live sessions over there. Thank you for your attention and see you in the next video.